Structural design and drawing of foundation and retaining walls. In previous class, we have discussed about what are the IS 456 recommendations for the designing of shallow foundations. Now, in this class, we are going to discuss about what are the design steps we have to follow to design a combined footing, whether it's a triangle, whether it's a rectangular footing or trapezoidal footing. Only the difference is we have to match the CG according to the shape of the footing. So let me take you through the design steps for combined footing. First one is we have to calculate the area of footing. I already mentioned about the area of footing, how we are going to calculate in IS 456 recommendations. By knowing the soil bearing capacity, so in the IS 456 recommendations, I already told you that the area of footing is such a way that it does not allow for the settlements need not to go beyond the permissible limits, and soil under the footing should not fail in the shear. So in that way we have to design the area of the footing. For that, the primary criteria is we need to know what is the soil bearing capacity. So by knowing the soil bearing capacity, and we calculate the load that are coming from the column on the footing, so the area the load by the area of footing value should not be greater than the SBC of the soil. So we know the SBC in that equation, and the load coming from the columns we know. So to find the area of the footing, so just divide the load from the column with SBC of the soil, we get the minimum area of the footing. So that is what I have written here. Calculate the total load by adding the loads coming from the column. Because this is a combined footing, we have more than one number of columns, so you have to add those, how many loads are coming on to the footing. So then anyway there will be a self weight of the footing also. In the before design, we don't know what is the depth of the footing and what is the area of the footing, so that we need to assume the weight of the footing as 10% of the loads that are coming to the footing. For example, if one combined footing is supporting two columns, from one column there is a 60 kilonewton load is coming, and from other column there is 80 kilonewton load is coming. So total load is 140 kilonewton. So we have to assume the weight of that footing as 10% of the total load. That means in this scenario, the 14 kilonewtons we assumed as the weight of the footing. So it is an example. So then the total load on the soil is load from the column plus weight of the footing. So we know the safe bearing capacity of the soil. As I already explained you, the area of footing is W, that is total load on the soil, which comes from the column and the weight of the footing, and divided by safe bearing capacity. By this we are going to decide the area of the footing. Then we need to define the position of the columns on that area of the footing. The primary aim to design to design combined footing is the CG of the footing must be coincide with the loads that are coming to the footings. For example, if you look at the shape, this is the plane of the footing. So because it is in rectangular shape, the CG of the rectangular will be in the at the center of the rectangle. So this is the CG of the footing, and there are two columns are resting on the footings. So from one column W1 load is coming, from other column W2 load is coming. So we have to find the CG of these two loads. So how we are going to find the CG of two loads? You have already gone through the strength of materials. In that course, you are going to calculate the CG of particular shape. So usually, if you need to find the CG of these two loads from one reference point, that is W1 into the distance of the W1 from the reference point plus W2 into the distance of W2 from the reference point by sum of two loads. That is what we are going to calculate. Now we need to calculate the CG from this center of one column. That is, if you if you calculate the CG of two loads from the reference of the center of this column, then the formula will be W2 into L by W1 plus W2, because W1 will be acting at the center of one column. So that definitely the distance between W1 the center of the column will be 0. So it will definitely get eliminated. So from the reference point of W1 column to the W2 column will be the L. So that is W2 into L by W1 by W2. So this CG1 and CG2 must be coincide. So in that so you have to coincide this CG1 and this CG2. In that way we have to place those columns. So by placing those columns, we can calculate the what is the distance from the center of the column to the edge of the footing, and from both edges of the footing. So the primary criteria is in the designing of combined footing is we need to coincide this CG1 and CG2 in such a way that we have to place the two columns on the footings. So that is the primary, that is the aim, to get uniform pressure distribution under the footing. So if you get the uniform distribution, then we can get the uniform upward pressure to the footing. So that is the primary aim. We have to get the uniform pressure distribution under the footing. So that to arriving that, we need to coincide that CG1 and CG2. Next one in the topic is we need to calculate the net upward pressure from the soil. So we know the loads coming from the column, and we know the area of the footing, that is by calculating from the previous step. So from that we need to calculate the net upward pressure. So pressure means the load by area. That is what we are going to do. So total column load by area provided. So total column load means the previous example where I told you 60 kilonewtons, 80 kilonewtons, so 1.140 kilonewtons by the area of the footing we have to do. From that we can calculate the net upward pressure. From the net upward pressure, we are going to calculate the net upward pressure per unit length. So this is the formula for that one is net upward pressure into width of the footing. So where we are going to use this pressure per unit length. So that pressure per unit length we are going to use in checking for the footing in one-way shear. Because we are in one-way shear, the reinforcement will be placed along the length. So we need pressure per unit length in the direction of the width of the footing. So that we are going to check the reinforcement per meter length. So in that scenario, we are going to use the pressure per unit length. So now we know the what is the pressure, what is the net upward pressure from the soil and the footing. We know from this step. So next we are going to calculate the shear force and bending moment diagram. If you look at this diagram, this is combined footing which is supporting column A and column B. So if you draw the free body, if you see the elevation of side view of this footing, so this is the bending profile of the footing. So don't take this seriously. So we have two columns at the edges of the combined footing. So it is look like a overhanging beam. So we need to solve this as a overhanging beam having 2 point loads, and in the negative directions there is a positive upward pressure. So by taking this as a overhanging beam having 2 point loads and 1 UDL, so you have to solve the bending moment and shear force diagram. So this bending moment I already told you, at the edges of the column there is sagging moment, and the middle of the footing there is a hogging moment. So here we need to find the reinforcement according to this maximum hogging moment, so that we need to place the reinforcement at the top layer. Here for the sagging moment you need to use this moment, and you need to place the reinforcement at the bottom layer. So this is the basic RCC thing. So I think you already studied in RCC. So that is it. Calculate the shear force and bending moment. So I already told you in mid-span footing we will experience hugging, and the overhang part we experience the sagging moment. Next, after calculating the bending moment and shear force diagram, we need to find the depth of the footing. So we have the maximum moment we are going to calculate from the bending moment profile. So we have to use that maximum moment to find the depth of the footing. So this you already know. From the depending upon the steel we are going to use, there is XU limit by D values in IS 456 page number 30. I already mentioned here, so that you can check once the class is over. So if you substitute this value into MU values, you already know what is the MU in the compression or tension. So here it is in FC, in the terms of FCK. You substitute this value in moment of resistance in the compression. You already know MU limit equal to 0.36 FCK BD into FCK BD into 1 minus 0.2 XU by D. So in that, if you substitute this one, these values will arise. So by using this moment value, for suppose we are going to use Fe415 steel, you are going to use this moment value. So moment you already know from the bending moment profile. Here FCK, you know the grade of the concrete, and here you know the width of the foundation. So you have to calculate the depth of the foundation. By this formula, you are going to calculate the depth of the foundation. Once we calculate the depth of the foundation, whether the depth of the foundation is sufficient to take care of the punching shear, we have to check. If you look at this diagram, I already told you the critical plane for the punching shear is at a distance of D by 2 from the face of the column. So the punching shear at this perimeter, the punching shear is acting at the column. So we need to consider this area to check for the punching shear. So here A naught is the breadth of the column plus D by 2 plus D by 2. That means the breadth of column plus depth of the foundation. Here the width of the length of the column plus depth of the foundation will give the B naught. So this area this perimeter we have to consider for the checking of the shear punching shear. So usually we check the punching shear near heavy column. For example, if a column is carrying 60 kilonewtons, the other column is carrying 80 kilometers. Definitely, the 80 kilonewton carrying column we know it as a heavy column. If the footing is sufficient for heavy column, then it is also sufficient for the light column also. So we need to check the punching shear for heavy column. So the punching shear force is, W is the weight coming from the column that is acting downwards. The net upward pressure is acting upwards. The resultant punching force will be W2 minus P naught will be in Newton per meter square. To convert that into newtons, so you need to multiply with the area. So I already told you this area will be the crucial for the punching shear. So we need to consider that area only, A naught into B naught. Then we need to factor that punching force by multiplying with 1 by 2. This punching force we need to use to calculate the punching stress on the column. So the punching stress will be, the punching force will be acting in that perimeter and the depth of the column. If the depth is sufficient, then it is sufficient for the punching shear also. So here the area will be the perimeter into depth of the column. So perimeter of the rectangle or square is 2 into breadth into length into depth of the foundation. The permissible shear stress from the IS code is Ks into Tc. So tau c we can take as 0.5 root FCK as for IS 456, and Ks value also taken from the IS 456 from page 72, class 40.2.1.2 according to depth of the footing. So there is a tabular column in page 47 which is having the relationship between Ks and the depth of the column. From that table we are going to take the Ks value. If the tau dash V, whatever the normal stress tau V, if it is less than tau dash V, then the depth of the footing is sufficient to take care of the shear, punching shear. If it is if it is greater than tau dash V, then we need to revise the depth of the footing by considering this value. So here from this formula you are going to calculate the revised depth. So this way we need to check the punching shear. Next, you need to calculate the longitudinal reinforcement calculations. So we have the moment at sagging, we have the moment at the hogging, we have the moment at second part of the overhanging also. So this is the formula that can be derived from a moment of resistance equations. So here you already know everything. Breadth of the column you can decide from the area of the footing. Breadth of the footing you can decide from the area of the footing. And the depth of the foundation we already calculated in the step 3. So use the depth and use the breadth of the footing, and you know the moment at sagging. So to calculate the AST for sagging moment, you need to use the moment at sagging, and you need to find the AST, area of steel, for the hogging part of the foundation. You need to use the hogging moment for in this equation. So you need to calculate the AST at different portions of the combined footing. After the calculation of this is what I already mentioned for your reference. If and all if you forget about my statement, so you can see this one. So after calculating the reinforcement calculations, we need to check for one-way shear. So the one-way shear I already mentioned in the IS 456 recommendation. The critical section for the one-way shear is at the distance d from the face of the column. Here also we are going to check the one-way shear for the heavy column only. So by knowing the critical section for one-way shear, first we need to calculate the shear force at the critical section. So shear force just right to the column. So here we will have the two shear force. If you look at this this diagram, so this value is the shear force just left to the column, and this shear force is the shear force just right to the column. Why we need to consider the shear force just right to the column is the critical section is at the right side of the column. So we need to consider the shear force just right to the columns, not the just left to the column, because we are considering the critical section for one-way shear is in the right side of the particular column. If we are considering if the heavy column is this one, then we need to consider the shear force just left side of the column, because here the critical section will be at the left side of this column. So that is the basic funda of calculating the for taking the shear force at just right to the column. So I am considering this is the heavy column. So I am considering shear force just right to the column. And P, I already told you, the P is net upward pressure per length into length. Length is D plus B by 2. B is the breadth of the column. So by this way we can calculate the shear force which is governing one-way shear. Then we need to factor by using 1.2 by using 1.5 factor, by giving some factor of safety. From using this VU value, we need to calculate the nominal shear stress by using VU by B into D. So that is the nominal shear. So you have a table 19 at IS 456. So you need to calculate the percentage of steel we have already provided. That is percentage means AST by area of the foundation. So percentage of the steel, and with the tau C there is a percentage of steel with the grade of the concrete. There is a in a table 19, we are going to take the tau c value. From the tau c value, we are going to calculate the tau dash v by using this formula. I already mentioned in that punching shear also. Then the same way we have to calculate. So the same way, if the tau v is less than tau dash v, we need to provide the minimal shear reinforcement by using this formula. If it is greater than this value, then we need to provide the shear reinforcement by using this formula. With this, we are done with the longitudinal reinforcement. Then we are going to calculate the transverse reinforcement. So if you look at this profile of the combined footing, in the breadth, in this portion, the foundation will bend like this. In the lengthwise direction, we are already used to calculate the longitudinal reinforcement. To calculate the transverse reinforcement, we need to consider this profile of the bending. So if you look carefully, so from here it is act like as a cantilever part. So the critical section for transverse reinforcement is the face of the column, because the face of the column will be act as a support for the cantilever beam. You already know the moment will be maximum at the support for the cantilever beam. So the face of the column will act as a cantilever support, and remaining part as a cantilever beam. So this is the face of the section. So I already told that the face of the section will be act as a critical part of transverse bending. So whether the transverse bending we can observe all over the length means no. The transverse bending will be observed in this portion only. So that is from the face of the column d distance, we are going to observe the transverse bending. So the total length of the transverse bending observed area is b plus 2d. So here b is the width of the column, and d is here in this direction d and this direction d. So 2d. So b dash will be b plus 2d. Now the area subjected to the transverse bending is the width of the foundation and this length of the section. So we calculate the area subject to the transverse bending by using b into b dash. So here I already mentioned the formula. B dash is width of the column plus 2 into d. Now the network pressure, for calculating net upward pressure, we need to use this area. Earlier we used b into d because we consider total width of the foundation is affecting for the net upward pressure. In transverse direction, only this portion is affecting for the net upward pressure. So by considering that assumption, we are going to calculate net upward pressure using this formula. So I already told you the foundation is act as a cantilever one. The moment for the cantilever beam at the support will be W into A square by 2. So here W is the net upward pressure. So the factor moment is 1.5 into M. So use this factor moment to calculate the AST, which I already discussed in the finding of longitudinal reinforcement also. Here the MU will be taken of this one. Here B is, I already told you, the transverse reinforcement we are going to place in lengthwise direction. So we consider B as a 1 meter. So for 1 meter length, we are going to calculate the AST of that one. So to because we don't know the how much length we are going to provide the transverse reinforcement, right? So if you calculate the AST per meter, then we can convert them into whatever length we are going to place the transverse reinforcement. So for that purpose, we are going to use B as a 1000 mm, that is 1 meter. So that is what I mentioned here. With this, we have completed the design steps of the combined footing. In the next class, we are going to see one example problem. Then you can use these steps and the problem. You can solve one assignment I am going to give after the next class. See you soon. Thank you.